All right, let's dive in. Today we're tackling multi-stage pumps. The workhorses behind clean water, manufacturing, all sorts of essential processes. We've got a ton of research and case studies to unpack.
Yeah, these pumps are fascinating. Using multiple impellers, like in series, to boost pressure incrementally, it's pretty clever for high pressure applications.
But I imagine more components also means, well, more things that can go wrong, right?
Exactly. More potential points of failure.
So, okay, imagine this. You walk into a plant, and a multi-stage pump just isn't delivering the pressure it should. What's the first thing that pops into your head?
Well, air entrainment is a common culprit.
Air entrainment.
Yeah, it's like, think about trying to drink a milkshake through a straw full of air. You're not getting much milkshake, right?
Right.
Same idea here. If air gets trapped in the pump, it messes with the flow, makes the pressure unstable.
So it's not just about the pump itself, it's about the whole system around it.
Oh, absolutely. You got to check for leaks in the suction line, make sure the pump's properly primed, full of fluid before you start it up.
Okay.
And sometimes installing air release valves can help. They automatically vent any trapped air.
Smart.
Mm.
But what if you've checked for air
Yeah.
and the pressure's still low? What then?
Well, then we got to consider wear and tear. Those internal components, the impellers, bearings, wear rings, they work hard, and over time they get tired.
They lose their oomph.
Exactly, like a marathon runner hitting the wall.
So these pumps need some TLC as they age.
Oh, absolutely. Regular inspection is key. You're looking for signs of erosion, pitting, scoring on those components. Anything suspicious, it's time for a replacement. Think of it as a tune-up, Get that performance back.
Makes sense. Now, there's also this thing called suction head. I've heard that can affect discharge pressure too.
Right, suction head. Basically, it's the force pushing the fluid towards the pump's inlet. So if the suction head is too low, it's like trying to suck a thick smoothie through a tiny straw. The pump's got to work harder, and that can lead to a drop in discharge pressure.
So proper suction conditions are key. How do we make sure we've got those?
Leak detection is crucial. Again, even a tiny leak in the suction line can really mess with suction head. Also, make sure the pump is positioned correctly, relative to the fluid source. Sometimes just a little adjustment in height or distance can make a huge difference.
Interesting. So low discharge pressure, lots of potential causes there. What another common issue we should watch out for?
Excessive power consumption. That's a big one. Not only does it hit your energy bills, but it can also be a red flag that something else is going on.
So if the pump suddenly becomes an energy hog, what should we investigate first?
Well, mechanical misalignment is a prime suspect. If the pump shafts and impellers aren't perfectly aligned, it creates friction. And friction loves to eat up energy.
Like trying to ride a bike with a wobbly wheel.
Exactly. Takes way more effort to keep moving.
So precision alignment checks during installation and after any maintenance, that's got to be super important.
Absolutely. And don't forget about the best efficiency point, or BEP. That's the sweet spot where the pump operates most efficiently.
Okay.
Running a pump too far from its BEP, it's like driving a car in the wrong gear. Burning more fuel, not getting the performance you need.
So it's not just about getting it running, it's about getting it running smart.
Exactly. Optimizing the hydraulic conditions, things like impeller sizing and trimming, that can make a big difference in ensuring the pump runs closer to its BEP.
Yeah.
Maximizes efficiency, minimizes energy waste.
Right, right. Now, we talked about wear and tear earlier. Bearings, they can wear down too, right?
Oh yeah, bearings are essential. They let the pump rotate smoothly, reduce friction.
Okay.
But if they're damaged or not properly lubricated, well, it's like throwing sand in the gears. Increased friction, more power consumption.
So regular bearing inspection and lubrication are must-dos.
Absolutely. Follow the manufacturer's recommendations for lubrication type and frequency. And if you see any signs of wear, don't hesitate to replace those bearings. Happy bearings, happy pump, and a happy energy bill.
Okay, so we've talked about air, wear and tear, suction head, misalignment, bearings. What else screams pump trouble?
Well, you know how some vibration is normal for a running pump?
Yeah.
But excessive vibration, that's a big red flag.
Right.
It can lead to serious damage, even catastrophic failure if you ignore it. It's like, think of driving a car with a wobbly wheel,
Oh, yeah.
Not only is it uncomfortable, but it could lead to a major accident if you don't get it fixed.
So if we see a pump vibrating like crazy, where do we even start?
One common cause is imbalanced rotating components. Think about the impellers, the shafts, spinning at high speed. If their weight distribution is even a little bit off,
Yeah.
it creates the centrifugal force that can shake the whole pump. Like a Have you ever seen a washing machine go haywire during the spin cycle? It can vibrate so violently it walks across the room.
Yikes. So how do we make sure those components are balanced?
Balancing, it involves specialized techniques, equipment to adjust the weight distribution of the impellers and shafts. It's really a job for a pro, someone with the expertise and the tools to get it right,
Right.
like a finely tuned instrument. Even a tiny adjustment makes a big difference in performance.
Okay, so we've checked for imbalanced components. What next? Still on the vibration trail here.
Gotta check those bearings again. Loose or worn bearings, they can cause instability in the rotating components, and that means vibration. It's like a loose wheel bearing on a car. You get that rumbling noise, maybe even the steering wheel shakes.
Oh, yeah, yeah. Those bearings are key for smooth operation. Anything else that can cause a pump to, well, shake, rattle, and roll?
One more culprit we got to talk about, cavitation.
Cavitation. Okay, now you're just using big words.
It might sound sci-fi, but it's a real thing, and it can cause some serious damage.
All right, I'm listening. What is cavitation?
Picture this. Tiny bubbles forming in the fluid as it flows through the pump. These bubbles happen because of a drop in pressure, and when they collapse, they release a shock wave. And that shock wave can erode the impeller, other parts, over time.
So it's like a tiny little implosion happening inside the pump.
Exactly. And those tiny implosions, they can cause big damage. The noise they make, it's often described as a crackling or rattling sound.
And what causes those cavitation bubbles to form in the first place?
It often comes down to inadequate suction conditions or maybe incorrect flow rates. Remember when we talked about suction head?
Yeah.
If the pressure at the pump inlet is too low, it can create these low pressure zones, and that's where those cavitation bubbles form. It's kind of like stretching a rubber band too far. Eventually it snaps.
Right, right. So got to make sure there's enough pressure at the inlet. How do we measure that, though?
That's where NPSH comes in, net positive suction head. Basically, it's the minimum pressure you need at the pump's inlet to prevent cavitation. A safety margin for pressure, you could say.
Okay, so we need the NPSH available in the system to be higher than what the pump needs. Where do we find that information?
You can find the NPSH requirements for your specific pump in its documentation. You really got to pay attention to those specs.
Got it. Besides paying attention to NPSH, anything else we can do to prevent cavitation?
Sure. First, make sure the suction line is clear, no blockages restricting the flow. And second, make sure the pump is operating within its recommended flow rate range. Running it too fast or too slow can cause problems.
So smooth and steady wins the race, huh? No pressure drama allowed. We've covered a lot here. Sneaky air bubbles, microscopic implosions. It seems like troubleshooting pumps requires, a detective's eye and a good set of ears.
You got it. But it's not just about reacting to problems. The best way to keep those pumps happy is with good preventive maintenance.
All right, let's talk prevention. What does a good preventive maintenance plan look like?
Think of it like taking your car in for regular checkups. Better than waiting for it to break down on the side of the road, right?
Right. So what kind of checkup does a pump need?
Well, first, you got to monitor those key parameters. Flow rate, discharge pressure, power consumption, those are the vital signs. You also want to keep an eye on vibration levels, bearing temperature, and seal condition.
Okay, lots to keep track of. How often are we checking all that?
The frequency really depends on the specific pump, its operating conditions, but a good mix of daily, weekly, and monthly checks is a good place to start.
Okay.
You might do a quick visual check every day, just looking for leaks or anything unusual. Then, weekly, you could check those key parameters, see if there are any trends or changes. And then monthly, you might do a more thorough vibration analysis.
Makes sense. What else should we be doing for prevention?
You want a structured maintenance schedule. Lubrication, cleaning, inspections, all at different intervals. Think of it as a layered approach to pump care.
Can you break that down a bit more?
Sure. Daily visual inspections, that's your first line of defense, just a quick workaround. Then, weekly, you bump it up to performance checks, measuring those key parameters, like checking the pump's vital signs.
Right. And monthly?
Monthly, you might do a vibration analysis. You'd need some specialized equipment for that. It helps detect things like imbalances or bearing issues that you might not see with just your eyes.
Okay. And we're about quarterly or even annually?
Those longer intervals are important too. Quarterly, you might focus on lubrication, making sure those bearings are happy. And then annually, it's time for the big one, a complete overhaul.
Overhaul sounds intense. What does that involve?
That's when you really get in there. You disassemble the pump, inspect every single component, and replace anything that's showing wear and tear. It's like a spa day for your pump.
Nice. So a good overhaul can really extend the pump's life, prevent those surprise breakdowns. It sounds like we've covered all the bases for keeping a multi-stage pump running smoothly. Anything else we need to remember for preventative maintenance?
Documentation. Keep good records of all your maintenance, repairs, anything unusual you notice. That information can be super helpful for troubleshooting and spotting recurring problems.
Love that. We're not just fixing pumps, we're learning from them.
Yeah.
Now, I'm curious, have you come across any interesting case studies or research that really highlights the importance of preventative maintenance? We talked about those advanced troubleshooting techniques earlier. Seems like we've moved beyond just like listening for weird noises and feeling for vibrations.
Oh, yeah, definitely. Those basic checks are still important, but now we have tools that let us really get inside the pump and see what's going on.
Like vibration analysis. It's almost like we're decoding the pump's secret language.
That's a great way to put it. Every component in a pump, it vibrates at certain frequencies.
Okay.
And by analyzing those frequencies, we can pinpoint problems. Think of it like a musical instrument.
Okay.
Each note, it corresponds to a different component, and a trained ear can tell when a note is out of tune.
So if we're hearing a sour note in the pump's vibrations, we know something's up.
Exactly. With vibration analysis, we're using sensors and software to listen to those vibrations, identify problems we might not even see, like having X-ray vision for your pump.
Cool. So can you give me an example of how that works in practice?
Sure. Let's say you're monitoring a pump, and you notice a spike in vibration at a specific frequency,
Uh-huh.
and that frequency happens to match the rotational speed of a bearing. That's a pretty good sign that the bearing is wearing out, or maybe it's damaged.
So the vibration analysis is giving us a diagnosis, not just a symptom.
Exactly. It takes the guesswork out of troubleshooting, saves time and money.
Awesome. Vibration analysis is pretty impressive. What about performance curve analysis? How does that help us?
Performance curve analysis, it's all about comparing the pump's actual operating data to its ideal performance. The performance curve.
Yeah.
Think of it as a map showing you the pump's expected flow rate, pressure, efficiency at different operating points.
So it's like a blueprint for how the pump should be performing.
Exactly. And by comparing the real-world data to the blueprint, we can see if there are any deviations, any signs of a problem.
Okay.
Like, for instance, if the flow rate is consistently lower than expected, even though nothing else has changed, well, that tells us something's not right.
So we're looking for any discrepancies between how the pump is behaving and how it should be behaving.
Yeah.
What kind of problems can performance curve analysis help us uncover?
Oh, all sorts of things. Worn impellers, internal leaks, blockages in the system, even improper impeller sizing. It helps us narrow down the possibilities.
Makes sense. Both of these techniques, vibration analysis and performance curve analysis, they rely on data, right?
Oh, absolutely. Data is key for troubleshooting and maintenance. The more data we have, the better we understand the pump, and the better we can prevent problems.
It seems like the future of pump technology is all about data.
It really is. Imagine pumps with all these smart sensors constantly monitoring everything: vibration, temperature, pressure, flow rate, all that data fed into a system powered by AI.
So the pumps could diagnose themselves.
Exactly. The AI would be analyzing the data, looking for patterns, anomalies, predicting problems before they even happen. Imagine getting an alert on your phone that says, hey, the bearings in pump 3 are wearing out. Better schedule a maintenance check.
Wow. There are no more surprise breakdowns.
Oh,
We'd
yeah.
be moving from reactive maintenance to like proactive predictive maintenance.
Exactly. It would revolutionize pump care, increase efficiency, reduce downtime, save money.
That's an exciting future. We've learned so much about multi-stage pumps today, from the basics to like the cutting edge of AI.
It's been a great deep dive. Remember, keep learning, keep those pumps running smoothly.
Thanks for joining us, everyone. We'll be back next time with another fascinating deep dive. Until then, keep those pumps humming.